Draft science video. So I found this Feynman clip that I hadn't seen before, part of some BBC program in 1964. Quality isn't very good, and it's about this -3 particle thingy, whatever the hell it was. Anyway, I didn't find that all that fascinating, but this commentary at the end by Feynman I did find somewhat interesting. So I figured I'll play it and comment on the commentary. Right. So, let's see if this is loud enough.
What does it mean? What is the significance of the fact that nature seems to obey this rule? I think today nobody knows. We'll only know, really, when we completely understand, or more completely understand, the fundamental laws of interaction of the nuclear particles. And this is a vital step forward to that understanding.
Alright, so it really has to do with this idea that there's a similarity, a symmetry they call it. But I mean, you're just talking about basically similarities. When they say physics say symmetry, they're basically saying similarity between these particles, and that they can essentially fill in for each other. Maybe temporarily, it'll work for a while, maybe that kind of thing. So something else besides a neutron can be a neutron, something can be a proton, that kind of thing. And it'll work for a while. You get away with it, maybe. I don't think, the atomic weights don't sometimes work out, so I don't think it'll be a very stable atom. But it'll get by. So that's what he's talking about. So part of the standard model has all these particles in it. They have found that they have proportional relationships, and this one was the apex of a triangle of a delay in decomposition. Let's call. I don't know what the right word would. Well, anyway, there would be a time delay, and there was a progression of the decomposition of particles in these accelerators. And so they kind of found a pyramid to this decomposition. It's probably the upside down pyramid, in that the -3 particle is really the particle shooting up the pyramid rather than going down, but who cares? Anyway, so these are quarks, I think. We're to call it quarks now, but it doesn't really matter.
But it isn't the understanding itself, and until we get that, we'll not really know the meaning of this, the fact that nature seems to obey the rules guessed at by Gell-Mann and Neyman.
Right, so they're just talking about the fact that, like they said, they had all the pieces of the pyramid except for the piece at the top, so it seemed kind of obvious that the piece was missing. But none of this has anything to do with necessarily anything real. This has to do with what's created in particle accelerators, which may not have anything to do with anything because it's not real. It's not a real circumstance. Smashing two cars into each other doesn't necessarily create coherent car parts.
It's analogous to the discovery of the periodic table by Mendeleev a century ago. He discovered at that time that various chemical elements came in families and that there were relations among them, that the chemistry of sodium and potassium, for example, were similar. This was extremely important in the development of science and bringing...
Yeah, it's sort of an interesting subject, just because the periodic table sort of is still kind of incomplete. I mean, it doesn't look right. You know what I mean? It doesn't have the flair of something symmetrical. It seems very unsymmetrical in some ways, and it doesn't seem to have any of that, like maybe there's a better way, like they haven't found the right way to connect these atoms in terms of their properties. Because that's really what we're talking on. We're saying that there's a class of atoms that have properties consistent with each other in columns and rows, and maybe it requires more than just two-dimensional ways of looking at it. I mean, they have colorized the periodic table too to indicate more dimensions. But yeah, these dimensions of similarity are kind of tricky. What causes what property?
About the ultimate understanding of the behavior of atoms. But the real understanding of the reason why sodium and potassium were similar, why the periodicities among the chemistry, in the chemistry of the various elements existed, could only come with the 50 years later with the knowledge of atomic physics, and this knowledge required a complete transformation of ideas about nature, a complete change of the philosophical position. Ideas that were impossible to appreciate at the time of Mendeleev. The principle of uncertainty of Heisenberg had to be discovered.
Yeah, right. But that's sort of where this all goes wrong. So he's gonna talk about where it goes wrong. And in this documentary, it was kind of joked in all the interviews with the different scientists about how theoretical physicists kind of petered out after they were 35 years of age. Like somehow theoretical physics is a young man's profession. That somehow you got retarded as you got older, as you got more mature in physics. You somehow lost your capacity to see the obvious even. And I think that's an interesting subject here in this context, where I would argue that that's what's the real problem is that they're in a box, okay, and they have to think outside that box because it's the wrong box. They're in the wrong box. Heisenberg is the wrong box. All this photon magic is the wrong box.
Whole understanding of the relation of cause and effect had to be modified with the principle of indeterminacy. And so it's going to be...
Right, so there is no principle. That's, again, this is the wrong box. Okay, it is determined. It's just that we don't have the microscope to see it yet. But there's no... the probabilities are rigid, and they're rigid because the mechanism underlying it is not indeterminate. It's quite determined.
Yeah, we will not understand really how nature makes this rule. Until we understand the nuclear interactions, and we won't understand those, I'm sure, without a deep and profound transformation of ideas somewhere along the line.
So, there he's saying it. I mean, he's saying a transformation of ideas, and this is the guy, again, like I said, who just sloughed off kinetic theories of gravity. I mean, force law that was an explanation of force. A force explanation that was material. And he ignored it. And, just validating the very thing he's arguing against is this idea that you have to, if you're going to do something, the biggest liability is wrong assumptions. That should be like the first thing people assume. Is you really got to watch in theoretical physics. Yeah, you got to really watch what you're assuming to be a fact, not because it's persuasively. The evidence should be. I don't know what to say. I mean, it's almost back to the stupid quacks like a duck kind of thing. I mean, there's a certain rule of, even if it makes sense one way, but it makes absolutely no sense in another way, that should be, a little red flag should go up, and you should say, okay, even though the math fits, math is a little funky sometimes, and you shouldn't be fooled by it. Because it looks like waves doesn't mean it has anything to do with waves.
We already see some of the difficulties. This law of Gell-Mann and Neumann, this symmetry law, is not a perfect symmetry. If it were, the statement would be that the replacement of one particle by another will make no change. For example, the replacement of a neutron by a lambda should make no change. And yet the neutron and lambda differ in mass alone by some 20%. So there alone is a change that when you take a neutron and replace it by a lambda, the mass is different. So this symmetry is not perfect. It's an imperfect symmetry.
Right. It likely has consequences. So, yeah, like I said, it's the fact that the mechanisms are similar. So it's like solar systems, it would be the argument I'm making. So what I'm basically saying is when they're accelerating these particles, what they're doing is throwing solar systems at solar systems. And you can just imagine the chaos that's created in that process where, depending on chance encounters, but they're all going to be probabilistic in the end. If you do it 1,000,000 times, there's certain things that'll happen very rarely and certain things that'll happen reliably. Colliding things and then orbiting, like I said, if I throw a Saturn at a Saturn, the two Saturns could end up spiraling off together. It could get pulled out of the orbit of the sun quite easily. And so the point I'm making on the symmetry argument is that, yes, these solar systems can be similar. So you could have a solar system that's identical in every respect, except the Earth is twice as big. Now, that solar system would function slightly differently, but not very differently.
Happy with a perfect symmetry. To say something is absolutely true and absolutely symmetrical seems to be a succinct, simple, and elegant statement of a law of nature.
Yeah, one of the boxes these guys are thinking in, that I'd say is the wrong box, is they think neutrons and protons and electrons are particles. They think of them as things in and of themselves. Because even though they say the word quantum, even though they talk about quantum mechanics, they don't think of those entities being made out of these quantum, out of something moving, something full of energy.
If a thing were completely unsymmetrical, then there would be nothing to say. But by what kind of a view is a thing that is only partly symmetrical natural? Is a thing that is only partly symmetrical beautiful? Well, the artists say that in this camellia bush here, the artists feel that the camellia, in its partial but near symmetry, is especially beautiful, and far more beautiful than a perfect geometrical pattern. But physicists feel that a partial symmetry is an indication that some deeper and more profound description of...
Yeah, well, it's really not a partial symmetry, because it's more like a fractal kind of symmetry. I mean, there is a perfect symmetry in the sense of the formula is quite symmetrical, proportional. And it's just a matters on the number of rotations and the thickness of the rotations, whether the pattern is irregular or regular. The symmetry.
Nature is possible. That there's gold in Benzar Hill. So we got a peculiar thought to grapple with, this partial symmetry. We're kind of stuck. We need a new idea. Before we really get the nuclear forces understood, some great new idea is required. Looking for symmetry is an old one. Incorrect.
So I find that, just kind of ironic, because I like I said, I think the great new idea would be to recognize that this whole idea of explaining forces as magical attraction and repulsion, just magic, as if it just oozes this effect, that somehow there isn't something causing the effect, that somehow it's just a manifestation of its existence, that, that there isn't a mechanism, a thing. That was just a huge box mistake. You put yourself in a box, that you're not going to find the truth in.
He suggested it, Einstein used it, really came into its own when quantum mechanics was developed. But the only information that we're accumulating, the places where they were really getting stuck, understanding the relation of these particles, is somewhere where we're missing some important, great idea. We have some prejudice that's in our way. That's the way it always is in these pinnacle discussions.
It's just so ironic, right? Some prejudice in our way. And you demonstrate your prejudice, when you looked at Lesage gravity, a kinetic gravity theory, and, didn't use any imagination at all. You just said, look, this is the easy way for me to say discount this, because I'm going to say this is what it is. It's a physical body moving at some either faster than light or slower than light, and that it degrades and through the interactions. You didn't really make it kinetic. You didn't use physics. Physics is a place where there is no friction. Physics is a place below heat. It makes heat. Yeah. So the process exists where there is no heat. And the process creates the byproduct of heat. and it's creating that heat out of something. And it's like you just weren't willing to understand what you weren't trying to make it work. You were trying to make it fail. And that's a huge problem if you're going to seek the answer.
The big pile-up of stuff, all the old things that you've thought of before, you try again and again. But the great discovery always involves a great philosophical surprise. The pinnacle...
Yeah, right. So there won't be, like I said, the surprise was is that you pretty much had the answer 300 years ago, and you kept pushing, like garbage sticking out of the can. You kept pushing it down, and it wanted to get out, and you wouldn't let it get out, because for some reason this didn't appeal to you.
Discovery isn't so much a fact as that it's possible to look at nature in a thoroughgoingly different idea. How strange it is, listen to this. How much is known after 200 years of studying physics? How much is known about the electrons, light, everything? And in order to understand the nuclear forces, it's almost certain that we're going to have to take a completely different view about everything that we know already. Philosophically, that is.
I mean, he's saying it. I mean, it's just so funny. He's saying we have to take a completely different view, and this was a guy that just said things like, just do the math. I've already thought about it. You're not going to figure it out. This is what he said later. So, you know, here he was still, you know, pondering. And, like, I think his lecture, when he dissed Lesage gravity, was 67. So 3 years after this video, he wasn't so interested anymore in trying to find an answer.
We're going to have to find another way to look at the world in which everything that we've already found out about it is the way it is. And yet that little detail about what goes on in the nucleus...
Right, exactly. The little detail is that the whole thing is just an exchange of directional information. That all movement and velocity happens inside of something itself. It changes. The thing changes. Interior. So when something's moving through space, it's not moving by momentum. It's not some magic thing that keeps it moving. It's moving because it has more directional energy in the direction it's going. It has more arrows pointing that way, so to speak. More quantum arrows of directional information moving in that direction, and that's why it's moving in that direction, and that's why it continues to move in that direction until something takes away those arrows, takes away that directional information. We're driven by directional information, and what direction is dominant in you will decide where you're going. Period. It's not pushing in any literal sense. It changes your shape internally. The atoms change shape, and when they change shape, they move.
Then falls into place.
They move like this. Moves. Okay, they're not rolling on a surface, but they're moving more in one direction than they are in the other direction. More in this direction, less in this direction. That means it'll go that way. That's what's happening. Very simple.
It's a very hard job. It's lots of work.
Well, it's just... I suppose it's lots of work when you're juggling a whole bunch of detail. So that might be part of the problem. You know, physics gets caught up in all of this detail. Calculus, complex, you know, the levels of the math even, you know, the idea that the math references other math. It's like you do one kind of math and then reference in that math another kind of math, and that becomes a variable in the math, and then that variable becomes a variable in the math. And so the math isn't straightforward anymore. It's a subdivision. It's math full of subdivisions, and any one of those being flawed will flaw the whole equation. And certainly none of those can be understood, all of those certainly can't be understood mentally as a model. It becomes really hard to mentally see an equation that has a cube, of a square, of a sine, of a, and see proportional relationships and why those numbers are relevant. It's really hard to see the length of the hypotenuse when you're doing the sine of an angle visually. So unless you have a model, the abstractions are really complex, and it's like the difference between just seeing a picture, seeing this image, and trying to describe this image, without any image.
What do we do it for? Because of the excitement, because of the fact that each time we get one of these things, we have a terrific El Dorado, we have a wonderful...
Yeah, it seems we have I'm smarter than anybody else, nah, 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 nah. I think there's a lot of that shit going on too. I fall into that too. But isn't that what it is? You're just, it's fun to go treasure hunting, and it's a kind of treasure the truth. And when you find a piece of it, it's fun. I found a piece. I'm rich.
New view of nature. We see the ingenuity, if I may put it that way, of nature herself, the peculiarity of the way she works. It takes a terrible strain on the mind to understand these things, and the real value of the development of the science in this connection, the thing that makes me go on.
Yeah. Well, like I said, this science in particular, physics, has gotten so obtuse, or obtruse, as he would say, obtruse, that, it's so incoherent to, anything understandable. It's just not understandable in the form it's in. And, I think that should say something to a physicist, like, no, it's saying it to him, right? And in 1964, he's feeling it. He's feeling this is too fucked up, and nature wouldn't be this fucked up.
Just the difficulty of understanding it. That these apes stand around and look at nature and find that to really catch on, they have to polish their mind to the very last. We live in a heroic age. We live in a moment.
Yeah, see, I just don't think you have to do that polishing crap. You have to do the keep the shit off of it thing. Yeah, you gotta keep the shit out of it. Garbage in, garbage out. And that's a big part of it.
That'll never come again. These discoveries cannot be made twice. One doesn't discover America 2 or 3 times in succession, really. And one doesn't discover the laws of nuclear forces or electricity more than once.
Well, that's a little bit weird too, because obviously I think you discover it in pieces, in a vague image, a foggy outline, and you can realize it's, you can sort of see that in truther science and other, a little bit of information is a dangerous thing sometimes, because it creates this image of something much grander or bigger or stranger, and then you realize it's just a shadow from a tree over there. It has nothing to do with a 7-foot monster you think you're seeing.
Some people say our age is meaningless. Those are only people who don't know what we're doing in this age. That this age is the age in which mankind is finding out about the nature that he lives in.
Yeah, well, this is a great truth, I would say, and unfortunately, I'd say that physics isn't helping anymore. It's just strangerizing it all and creating more fog than vision now. And that fog has just become a new religion. And, the real crude fact is that, yes, physics can tell us there's no free will. Physics can tell us we're programmed machines. Physics can tell us, that this whole evolutionary environmental interaction thing, okay, that's all it is. It's all just byproduct of cause and effect interaction, and that the fundamental mechanism is always going to have at its core this force law of attraction and repulsion, and ironically there's just repulsion and the illusion of attraction when repulsion is released.
They don't understand what's already been uncovered. They can't appreciate the search. What makes us so sure that the new discovery of the interrelationship between nuclear forces is going to be so wonderful? How do we know it isn't going to be some complicated, dirty, or simple thing? We don't know. We keep...
Yeah, well, he did kind of think it, so let's just say he doesn't know, but he did opine that he thinks something like the checkerboard will be revealed, that the basic mechanism is this simple thing. There's just a ton of it. A ton. A bigger ton than we thought. Like many tons times the speed of light squared kind of amount of tonnage. The density of the universe is many billions of times denser than was perceived.
Keep on trying anyway. Not sure. It's worth the risk, because it very likely will be peculiar, and if it is, it'll be very interesting. How long is it going to take? Do we have all the clues? Every time there's been a very great discovery, one can look back and say, why didn't we think of that before?
Yeah, exactly. And then, yeah, like I said, you fell right into the trap again. I mean, I would have wished I could have played this video back to you in 1967 when you were sitting there analyzing what was the truth.
Of course, there's a time so far before that you say, well, the reason they didn't think of it, they didn't have enough facts from experiment. Question. Do we have enough facts from experiment so that after this thing is discovered, people look back and say, why didn't they think of that before? How far before? In 1964.
Yeah. Well, again, you almost have too many facts from experiments, but your experiments would get so elaborate and convoluted and strange in themselves that you can't rely on what's causing the phenomenon. You're introducing so many variables. So if you go with the simple experiments, and you always take your experiments in a context and say, and recognize the fact that there are too many unknowns in your experiment. You don't know. I mean, they use all the time these mirrors and these laser experiments, and you're just, we don't even really know how a mirror, what it's doing to the photons that hit it, whether it's the same photons that are actually reflecting, and yet they assume it.
My colleagues don't agree with me, but I think this is the day. I think that we now know enough that if with a sufficiently clear reasoning we could come to the answer, or put it another way, when we do finally find the answer after the experiments have given us too many clues, a lot of extra clues, we'll look back and we'll see how a perfectly sensible, logical line of reasoning from the present position could have brought us to the understanding.
Right. I mean, ironically, again, somebody 300 years ago put on the table something that, yes, was flawed, because they didn't have nearly as much understanding of this frictionless kinetic world that existed for atoms, inside of atoms even. And nobody was really doing nobody took that simple logical step of saying what we're calling a particle, electron, proton, neutron, are not trons, they're systems. There's the neutron system, the proton system, the electron system. They're like solar systems. They're mechanical devices that are storing energy. And the energy is still in the form that we know energy to be in, which is moving at the speed of light. It's electromagnetic photons captured. That's what matter is. And if they would have just taken that simple step, then they could make kinetic theory of force law work, because you get rid of all the heat. You get rid of all these momentum issues that don't have anything to do with reality. There is no literal push. There's a change in configuration. There's an exchange of identity. Pieces of you that are going that way get exchanged for pieces going that way. It's just that simple. Really simple.
I wouldn't have said that before the discovery of the Omega Minus. That to me is
the Omega Minus. So that's what this video was really about. And so I just think this is very interesting, very revealing. But this was Feynman, right? I mean, he had his moments where he, you know, and then there's moments where you're just saying, man, you know, that's just so close-minded. So, you know, he had these times when he's talking as, you know, like I said, this is a guy you're saying, okay, he knows the problems, he knows the liabilities, he knows the dangers of becoming stagnant. And 7 years later, or 3 years later, he's stagnant. He's saying, just do the math. Don't think about it. If I can't think of it, and Einstein can't think of it, you can't think of it. Not as surprising.
the significance of this discovery.
Alright, so that'd be an Omega Minus. I think that's just, like I said, quirky, borky. But anyway. Sorry, it's not a regular video. I mean, it is regular in the sense that I got to my point of, like, this is related to force. I mean, forces are everything. The understanding that forces, that directional information is in the forces, and the forces are a byproduct of filtering directional information. When force, right now, gravitons, whatever you want to call them, go through me, they have to, if they don't exchange any directional information with me, yeah, then they go about their way right through me like I was invisible. But if they exchange information, then they go somewhere else, and the world changes. Again, the real paradox is just thinking about that X. And just think about the X. What is the X? Is this piece of the X going straight and this piece going straight? Or is this piece bouncing off this piece and going that way, and is this piece bouncing off that piece and going this way? Same exact thing. Same exact outcome. And just by perception alone, how you look at it, you can understand consequence. That if they're bouncing off each other, then you end up creating the square circle, so to speak. The perpetual trap. And that is the nature of matter. That's the first filter. And now that filters, when stuff comes through, it changes directional information with this thing, and this square starts to move in a direction based on what directional information arrows are hitting it. The pressure, there's a medium. Empty space isn't really empty space in the sense that, yes, there's empty space, but there's all of this directional information surrounding us. We're in a pressure gradient of it. And some percentage of it is pointed right at us and is going to hit us. And that means something. Yeah. Alright, I think I've done enough. Okay, till next time.